Now I'm gonna read in the next data file into my existing PFC because I've already got some plot items set up and everything. Let's just look at the next data file. File, open. I'm gonna go up one level into the to bounce directory. And here's this. Single ball falling onto a fixed wall under gravity. Let's run that. Here's the view. Let's get rid of the domain. Let's add the wall plot item. Now let's zoom in. So gravity is on and this guy is gonna bounce, right? So let's do cycle 5000. And here we go, it's bouncing, and there's a contact force plot item. So you can see the force, suddenly a force forms, it's directly compression, it's acting in the normal direction, everything is symmetric, so this just keeps bouncing up. Now, as we've been doing this, we were also, first of all, let me shut down that data file. And actually, I'm going to go up here and I'm going to give it the right finger. I'm going to say remove from project because I don't need it anymore. There. Now, we were monitoring a history. So this particular ball right there, ball create, we said give it an ID number of 5. So now I can say, oh, I want to monitor the Y position of ball number 5. And I'm going to give it a name, ball height. Okay. And so I can use the history plot item plus history chart. There's only one history to work with, Y position of ball 5. So boom. Let's turn off these other things. So the height, it's a 0.5 diameter ball and the wall is sitting at 0. So when it hits here, the height should be, the height should be 1 because where is this thing? Yeah, the ball started up as at 1, 1. Radius is 0.5. So at the top it's 1 and then it should go down to 0.5. So it should bounce between 1 and 0.5. So here's 0.5, here's 1. Notice that it's bouncing below 0.5 because it's overlapping the wall. And then the force is building up and it's pushing back. But look at the height. What is happening here? So if there's no damping, just think you have potential energy in this system. And so what happens is you have potential energy at the top, mgh, and then when it gets to the very bottom and the velocity reaches 0, all the energy is stored as strain energy in the spring, which then causes it to start going up again. So if energy is conserved, it should always bounce back to the same height. It's not doing that. This is worrisome. Now, why do you think it's not doing that? So think of this. That ball starts going down, and what happens? It just comes in contact and overlap starts happening. So here's delta, overlap. Overlap gets bigger and bigger and bigger, reaches a maximum depth, and then gets smaller and smaller and smaller, right? And because force equals stiffness times overlap, that means the force does the same thing. This is the compressive force. Overlap begins, force builds up, builds up, builds up, reaches a maximum, goes back. Okay. If we look at this force versus delta plot, though, then force versus displacement, that's the spring. There's a spring here, right? And it's storing strain energy. So what that would look like is this. Force would build up as delta gets more and more overlap. It reaches a certain maximum depth, and the area underneath this curve is the energy stored in the spring. Okay. Now, so if you actually resolved this collision with an infinite number of points where it traced this thing out, this is the energy stored in the system. But notice we're just based on our time step, we're sampling here, then we're sampling here, then we're sampling here. Okay. And so the area of this shaded thing is not necessarily going to exactly equal the true area under the curve. Like, for example, if this time step is too big, it wasn't even touching, and suddenly at the end of the time step, it already had an overlap of delta that was non-zero. And so right away, we're starting to introduce error. Now, if this hypothesis is right, as we reduce the size of the time step, this should converge to this here, and we should have the same energy stored in the spring at the bottom. Okay. And so let's actually demonstrate that. So now, first of all, well, let's do this. We're going to force the time step, the maximum value it can ever be, to be 1e to the minus 4, which is smaller than it's using now. So now let's look at this. Ball, wall, history. And now let's cycle. So first of all, it's cycling a lot slower because it's not because I'm taking super small time steps now. Okay. But it is going down. You can see it here going down. Let's not show the plot. Now, while we're looking at that, because that's about as interesting as watching paint dry, right? It's still, oh, look, wait, there we go. Notice it went up to the same height. Now you're going to see the force build up. You're going to see a bit more, right? And you'll have to trust me. It's going to keep going to the same height now. It's going to be conserving energy. Now this raises an interesting point we want to talk about here. So this is a collision problem. And for this particular problem, we want this collision to properly conserve energy and be correct. So what that essentially means is I need to, if you want that to happen, you're going to need to force the time step to be really, really small so that you resolve the collision, right? So that right when it's not touching to when it's touching, it's just barely touching. And then you can slowly build up the force like it's really going to build up during a collision. If you don't do that, the time step is not chosen based on a collision. That had nothing to do with it. The time step was based on how fast the system was vibrating. And so the time step is related to the mass and the stiffness. This would be an additional constraint on the time step if you wanted your collisions to be 100% perfectly accurate. Now, in most cases, that's not what you necessarily require out of a PFC. If you're doing like a geotechnical type system, you're going to have a collection of particles. You're going to turn on gravity. You want them to fill a box, and then you want to glue them together and look at what happens. Okay. If you run PFC by default, what it's going to do is that when it's bouncing around and coming to equilibrium in that box, the collisions are not necessarily exactly conserving energy, but we really don't care because we just want an arbitrary bouncing around and stopping to come to some initial packed state. Okay, so that's the point. Now the other thing we can look at here, so let's see how far did it go. Yeah, there we go. It's bouncing like we would expect. Let's just go, let's get rid of that. So we can just watch this thing run for a minute. And so cycle. All right, so now it's bouncing up and down. Da, 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 da. Let's stop this. Let's put on some damping right there. See, it says ball attribute damp of 0. Let's do a damp of 0.1. Now we'll run it. And so you can see now it's going to damp itself out. And it took a while for that to damp it out because my damping factor was only 0.1. The damping factor that we use in almost all cases is 0.7. And so there you'll see it's going to much more quickly damp itself out. And now it's just sitting there. Okay. Now, what is the magnitude of that force? Let's work this out because at this point, this should be in equilibrium. let's see in static equilibrium. So let's do shift escape. Let's see if it's in static equilibrium. Let's just say ball list attribute velocity. There, it's e to the minus 15. It's effectively 0. It's just sitting there. Okay. Okay. So what's the density? We know if we know the density and we know the radius, we should be able to compute the mass. And if we multiply the mass by the acceleration of gravity, here's gravity, 9.81 meters per second squared, we should get the force. Okay. So what we're going to do is you're going to help me do this, right? So force equals mass times acceleration due to gravity, right? And mass, what's mass? Going to be density. Oh, that's the wrong one. Density times volume, right? And whoops, times G equals, well, just do this. Density times volume. What's volume? That's the question. Volume equals force equals, so what's the density? What's the density? 1,000. So 1,000 kilograms per cubic meter. Whoops. So that's density. Let's see if we get all the units right here. Density times pi. See, work it out yourself if you can go faster than me. Pi, what's the radius? Radius is 0.5 meters. Squared. Times 1 meter, which is the thickness. Is we can say contact list question mark, contact list, and notice that one of the things is force. Contact list force. 7704.8. 7704.16. We're probably not quite in total equilibrium. Now we can also look at that if we go to the contact. Let's make a new plot item called a new contact plot item. Turn that off. So contact, shape cylinder, numeric value. Oh, come on. Numeric value. Where is force? Text value. Vector quantity force. There we go. Now I'm coloring it by, it's a cylinder, and I'm coloring it by a vector quantity, which is the contact force, right? There we go. 7704.8. That's what we get here, right? So that's a different way of looking at that. Yeah, good enough.